The mordell equation Fermat's proof. Let's have a look at a special case of the mordell equation, which looks at the difference between an integer cube and an integer square. In this case, we want to find all the integers x, y, such the difference between the cube and the square gives 2. These sort of problems are called Diophantine problems and have been studied by mathematicians for around 2,000 years. We want to find integer solution to x cubed minus y squared equals 2. First, we can rearrange and factorize using the property of imaginary numbers, wherein, as you can see in the picture below, are the solutions of how we can define an alpha and beta such that the alpha is equals to a plus b square root of negative 2 and the beta is c plus d square root of negative 2. Then we can get alpha and beta, wherein z is square root of negative 2. Completeness, we can say that the alpha and beta are part of an algebraic number field. Next, we use an extension of the prime power trick, which ensures that the following two equations have solutions if our original equations also has solutions. Therefore, we define y plus square root of negative 2 is equals to alpha cube, and y minus square root of negative 2 is equals to beta cube. We can then substitute our definitions for alpha into the first equation directly above and expand. Next, we equate real and imaginary coefficients to give where the picture shows below. This last equation therefore requires that either one of the following equations must be true. We take the case when b is equals to 1, we get 3a squared minus 2 times squared equals 1. Therefore, a is equals to 1 or a is equals to negative 1. If we take the case when b is equals to negative 1, we get b is equals to negative 1, a is equals to 1, or a is equals to negative 1. Therefore, our solution set is AB 1, 1, 1, negative 1, negative 1, 1, negative 1, negative 1. We substitute this possible answer into our definition for y to give. We can then substitute these two values for y into the definition for x to get xy equals 3, 5, and 3, negative 5. This therefore the only solution to our original equation. We can check they both work. X cubed minus y squared is equals to 2. 3 cubed minus 5 squared is equals to 2. And 3 cubed minus negative 5 squared is equals to 2. We can see this result illustrated graphically by plotting the graph x cubed minus y squared is equals to 2. And then seeing that we have our integer solutions 3, 5, and 3, negative 5 as coordinate on this curve. This curve also clearly illustrates why we have a symmetrical set of solutions, as our graph is symmetrical about the x-axis. This particular proof was first derived by Fermat of Fermat's last theorem fame in the 1600s and is an elegant example of a proof in number theory. You can read more about the mordell equations in this paper. The proof above is based on that given in the paper, but there is a small mistake in factorization so that y equals 7 and y equals negative 7 is erroneously obtained.